Hello everyone, welcome to the lecture series of pattern classification. I'm Kundan Kumar, and if you would like to have these lecture slides, you may refer to my GitHub page at this given link. So in the last class, we were discussing the boundary representation, and we have seen that how to compute the chain code and the differential chain code. And we have also discussed that the differential chain code is a rotation invariant. So here we are going to verify that is this differential chain code really invariant to rotation. So here we have this boundary pixels, and then we obtained the grid points. Then we have written the numbers associated with the line segment, and then we have written our chain code, and then this chain code is transformed to the differential chain code to make it rotation invariant. So this differential chain code is obtained by taking the first difference of the chain code, and then we make it independent of starting point so that our differential chain code has become the rotation invariant. So we will obtain this differential chain code which is rotation invariant for this shape. So now what we will do, we will rotate this shape at an angle of 90 degree in the direction of clockwise. Then we will obtain this type of the boundary image, and the same thing we will perform, okay, the same grid, okay. Then we will obtain this grid points, we will obtain these grid points, and then we will write the sequence of the numbers associated with the line segments. So that will be our chain code, and in the same process we will write our differential chain code, and we will convert that differential chain code as rotation invariant. That means we will make it independent of the starting point. So when we will verify these two differential chain codes, then we will find that these two differential chain codes are same. So it verifies that that differential chain code is invariant to rotation. But is the differential chain code is invariant to rotation at any angle? So here we have verified by rotating our boundary image at an angle 90 degree. So what if we will rotate our boundary image at an angle 30 degree? So in that case, whether it will be same differential chain code or not? Think on it and try to answer. So our next topic is polygonal approximation, and this approximation of the boundary. That means a boundary will be approximated using the line segments, and those line segments will generate a polygonal. Okay. So a digital boundary can be approximated with arbitrary accuracy by a polygon. In practice, the goal of polygon approximation is to capture the essence of boundary shape with the fewest possible polygon segments. So this polygon will represent the boundary. It totally depends on the grid size that we will select to downsample our boundary image. So if our grid size will be coarser, then definitely the more number of line segments will be required to approximate the boundary using the polygonal. Okay, so that's why it is arbitrary accuracy by a polygon. So there are two different approaches to find the minimum perimeter of a shape. So there are the two different approach. One is minimum perimeter polygon and splitting technique. Okay, so here first we will make the grid, or we will downsample the resolution of the boundary image that we have. Okay, and our objective is to make it, that means we have to convert this boundary in line segments, and those line segments will construct a polygon. Okay, because it looks like as a polygon. So the first algorithm is minimum perimeter polygon. So we are not going to discuss the exact algorithm to find the minimum perimeter polygon of any arbitrary boundary, but we will get the essence that how this algorithm works. So suppose we have a boundary, and this boundary encloses the region inside. Okay, so this is basically the dark gray. Okay, and this is light gray. So what we do, we first scan the corner points of the region. Okay, we will scan the corner point of the region, and we will denote the convex with white dots and the concave points with the black dots. Okay, in the counterclockwise direction. Okay, that means we will scan in the counterclockwise, and wherever we will find the convex point, that will be our white dots, and wherever we will find our concave vertices, okay, we will denote it as the black dots. Okay, so we will get this type of representation of the boundary. Then all the black dots will be moved to the opposite corner of that grid. Okay, so all the black dots will be moved to opposite corner of the grid, and that will be outward. Okay, that means outward of the region. Okay, in this way. Then we will join the dots, that means the mapped dots, and we will make our approximated boundary. Okay, so in this way we will get this kind of the approximated polygon, and this polygon will give us minimum perimeter polygon. Okay, next approach is splitting technique. This is also a kind of the polygonal approximation, where our boundary will be approximated using the polygonal. One approach to boundary segment splitting is to subdivide a segment successfully into two parts until a specified criteria is satisfied. Okay, so how this algorithm works: First, all the pixels on the boundary we will store in a list, and then we will find the two pixels which are at the farthest distance. So suppose we have the point A and B, okay, where these 2 points are at the farthest distance. Okay, and these, so basically if we will solve this problem using a simple distance calculation between each pair of pixels, then it will be very computationally expensive. So there are some algorithms which helps us to find the farthest point within a very short span, and that algorithm is called the KL transform. So once we will have the two farthest point on the decision boundary, then all the pixel values will be divided into two sets. One set will be on the left set and another will be on the right set. Okay, that means whatever the pixels are on the left side of this line, those pixels will be in the set left, and whatever the pixels which are on the right side of this line segment, that will be in the set right. Then we will find the distance of each point in the set left from this line segment A and B, and we will select the pixel which having the maximum perpendicular distance from this line segment. So suppose this point is at the farthest perpendicular distance from this line segment AB. So suppose this is C. Okay. Similarly, we will find the distance of each pixels in set right, and we will check that which pixel having the largest distance among all the pixels from the line segment AB. Okay, so if this pixel is at the farthest perpendicular distance from this line segment AB, then this will be our D. Okay, so then we will have this kind of representation. That means we will get 4 points on the boundary, and when we will join these 4 boundary points, then we will get a polygonal approximations where we will have the 4 line segment. So this polygonal approximation is for a closed boundary, and here we have seen that the best starting point is usually the 2 farthest point in the boundary. Okay, and the farthest point can be obtained by KL transform, and the maximum perpendicular distance from the boundary segment to the line joining its 2 endpoints not exceed a predefined threshold, and that threshold may be some fraction of the line length AB. Okay, so this is basically the splitting technique that we can perform to obtain the polygonal approximation. The next approach is signatures. So basically, signature is a one-dimensional representation of boundary. Basically, boundary is a two-dimensional representation. Okay, So it will be easier to define using one-dimensional representation of the boundary. So how we can define? Suppose this is our shape, okay, and we will have, suppose these are the boundary pixels, okay. So from these boundary pixels, we will compute the centroid of this boundary shape. So when we will compute the centroid, then the most probably we will obtain the centroid at this point when we will have a circular boundary. Then we compute the distance of the pixel location, okay, and its orientation with respect to the x-axis, which is in this direction. So suppose we have a pixel at this position, then this pixel can be denoted by the distance r, okay, and that is the radius of this shape and the orientation of this pixel, which is 0 here. Suppose we have another pixel here, so it will be at the same distance r, but the orientation will be theta. So we can draw our signature using these informations by taking the angle on the x-axis and the distance of boundary pixels from the centroid on the y-axis. So when we will plot the relation between these two parameters, then we will obtain a straight line for the circle, because all the pixels are at equidistance from the centroid. So this is basically the signature of a circle. That means a boundary which is a circle. Similarly, we can draw a signature for a square. So here also what we can do, so these are basically the boundary points on the square, okay. So here we can compute the centroid of these pixels, and it will be, suppose here, okay, then we will compute the distance of this pixel, okay, with respect to the reference, okay, the distance we will compute, and we will compute the angle with respect to our reference axis, which is in the x direction, okay. So we will have the pixel location, so we will compute the distance r, and we will compute the orientation or the angle of this pixel with respect to our centroid, where our reference is x-axis. So in this way we will compute r and theta for all the pixels on the boundary, and we will plot between theta and the distance r. So something like this we will obtain, which is basically the signature of a square. So in this way we can obtain the signature of any arbitrary shape, okay. So signature are invariant to translation but variant to rotation, because when we will rotate this square, then maybe our signature will change, okay. Maybe this will be our starting point for this shape. So signature is basically the variant to rotation, and how we can make it invariant to rotation? We have to consider the starting point as the farthest point from the centroid. That means we will start our computation from the farthest point from the centroid. Okay. For example, here we will start from this point. Okay. That means this will be our reference instead of this x. So in that case, maybe our signature will be invariant to rotation. That means we have to find the distance and we have to find the direction, in which direction the distance is maximum. Okay, and that will be our reference direction. And to make it scale invariant, we have to normalize our signature so that the values will be in between 0 to 1. Okay, because whatever the value, whatever the variations we have here, so these values should be normalized. It will be between 0 to 1. So we have to divide with this parameter. Okay, or by dividing by the variance of the signature. So either we can make it between 0 to 1, or we can divide the signature with the variance of the signature. But this will not work on the circle, because the variance of a circle is 0, because here there is no variation. Okay, it is 0. So in that case, when we will divide with the 0, then it will be undefined. Okay, that's why it is not applicable for the circle. So this is the two way we can make our signature scale invariant. Okay, there are some other approach for obtaining the line segments, or we can divide our boundary in the different boundary segments. Okay, that means we have to find the critical points on the boundary. So for that, we have to decompose a boundary into segments, and that is often very useful because it reduces the boundary complexity and it also simplifies the description process. Okay, whenever we will find the feature vector, so it will simplify that. So in that case, we can use the convex hull of the region enclosed by the boundary. Okay, and that is very powerful tool for robust decomposition of boundary. Okay, so let us see what is the definition of the convex hull. Convex hull H of an arbitrary set S is the smallest convex set containing S. So suppose this is our boundary image, okay, where this object is there and this is the boundary, and here S is the set where it contains the pixels which is enclosed by this boundary. So we can find a convex shape so that this S will be totally contained in this convex hull. So what is the smallest convex set? How we can find it? We will find the concave surfaces, like this is the concave surface. Okay, so we will fill all the concave surface on this boundary. Okay, so in this way we will fill all concave surface on this set S. So whatever the shape, whatever the set we will obtain, that set is basically the convex hull. Okay, and if we will take the difference of convex hull and the set S, which is the pixels enclosed by this boundary, is called the convex deficiency, which is denoted as D. Okay, and wherever it touches, okay, where it will be the tangent, okay, so those points will be considered as the critical points on the boundary, and that will divide our boundary in the boundary segments. So we can say that it divides our boundary in boundary segments. Okay, so there is another way to represent the boundary, and that is basically the skeleton of any shape. Okay, so we can perform the skeletonization, and that is we can obtain using the thinning operation. So this thinning operation is nothing but a morphological operation that we study in the image processing. There we find the medial axis of any shape, and that is why it is also called the medial axis transformation. Okay, we can also understand the skeletonization using the Pyre fire concept. And what is the Pyre fire concept? That if we have a piece of paper, and if we will burn from all sides, and we will assume that the paper is equally inflammable at every point, then what will happen? It will burn from all sides at equal rate. So wherever the fire points will meet, okay, from this side and this side, so these are the basically meeting points. So wherever it will meet, that will form our skeleton of this shape. Okay, so this much for the boundary representation. Now let us discuss the boundary features or descriptors. So we can define our descriptors using the boundary representation that we obtained. So there are many boundary descriptors like length, diameter, minor axis, even the basic rectangle. So how we can compute these? Suppose we have a boundary image. So here we are making the grid points. Okay, so suppose these are the grid points, so it will represent our boundary. Now we can extract these features. Suppose this is length, which is the simplest descriptor of this boundary. So it will compute the length of the perimeter. So how we can compute? So here we will count the number of horizontal grid, number of vertical grid, and root 2 into number of diagonal grid. So here 1 horizontal grid, 2 horizontal grid, 3 horizontal grid, okay, 4 horizontal grid, and 5 horizontal grid. So it will be 5 plus 1 vertical grid, 2 vertical grid, 3 vertical grid, 4 and 5. So we have 5 number of vertical grid plus root 2 into the number of diagonal grid. So here 1 diagonal, 2 diagonal, and 3 diagonal. So when you will compute this value, okay, so this will be the length of the perimeter, because here each grid is of unit distance. Okay, so this will give the length descriptor. We can compute the diameter. And how we can compute the diameter? So we will compute the distance between each pair of boundary points. and we will consider those two boundary points which are at the maximum distance. So here, if we will consider this boundary representation, might be possible that these points and these points, so distance between these points will be maximum compared to all other pair of boundary pixel pair. Okay, so that will give you the diameter descriptor. So the minor axis of boundary is defined as the line perpendicular to the major axis. So in this case, the diameter can be considered as the major axis and the perpendicular. Okay, so perpendicular, maybe this will give us the minor axis. Okay, as you know, in case of ellipse, we have major axis and minor axis, something like this. So this is our major axis and this is our minor axis. Okay, so the same concept came here to define the descriptors from the boundary pixels. Okay, we can define a basic rectangle. Okay, and that basic rectangle is formed by the major and minor axis encloses the boundary. So if you will see this ellipse, then the minor axis and major axis will enclose this boundary in a basic rectangle. Okay, so this is called the basic rectangle, and we can compute the eccentricity, which is the ratio of major axis divided by minor axis. Okay, so we can have the other boundary descriptor as shape number. So how we can compute the shape number? So the first difference as smallest magnitude that we defined in our Chan code. Okay, so the differential Chan code, which is the invariant to the rotation, that is our shape number, and the order of the shape is the number of digits in the shape number. Okay, so keep in mind that differential Chan code, which is rotation invariant, is equivalent to the shape number. Okay, so suppose here we have one boundary. Okay, so we can write the Chan code. So we can write this Chan code using 4 directional encoder. So it is 0, 1, 2, 3. So from the top left corner we will start. Okay, and we will traverse in clockwise direction over the boundary. So this is 0, this will be 3, this will be 2, and this will be 1. So here we have the Chan code 0, 3, 2, 1. And we can compute the first difference by taking the difference. So here we have number 0, 3, 2, 1. So we have to compute the first difference between these two digits. Okay, so we have to traverse from 0 to 3 in the anti-clockwise. So here 1 step, 2 step, and then 3 step. So it will be 3. Similarly, we will compute the first difference between 3, 2. So 1 step, 2 step, 3 step, and it will be 3. Okay, similarly for 2 to 1, then it will be 3. Okay, and then we will compute in the circular sequence. So 0 will be here, then we can compute the the first difference between 1 and 0. So it will be again 3. So this is our the first difference. Okay, and as I told you that the rotation invariant differential chain code will be our shape number. So how we can make it rotation invariant? So this is the first difference. Then we will consider largest or smallest number possible using these digits. So here all digits are 3. So this will be our shape number. Okay, this is the smallest or largest, whatever you can say. Let us see this example. Okay, so here we have to start from top left corner. So this will be 0, this will be 0, this will be 3, this will be 2, this will be 2, and this will be 1. So we have the chain code 0, 0, 3, 2, 2, 1. Okay, now we have to write the difference. Okay, so how we can write the difference? 0, 0, 3, 2, 2, 1. So what is the difference between these two? It is 0. Difference between these two, it is 3. This difference is 3. This is 0. This is 3. And we have to consider the first difference between last and first as well. Okay, so it will be 3. Okay, so this is our first difference. Okay, so don't bother that whether why it is different, because they have considered the difference this 3 at first. So we can write this one as well. There is no any issue. So this is our first difference. From this differential chain code, we have to write the rotation invariant differential chain code. So what is the possible smallest number or largest number? So here in the shape number, we have to consider the smallest number possible that we can construct using these digits. So when you will write these numbers in the circular sequence, this number will be your smallest. So that's why it is 0, 3, 3, 0, 3, 3. Okay, so now let us consider this. Okay, this shape. Okay, one more we will check. So this is our top left corner. So this will be 0, this is 3, this is 0, this is 3, this is 2, this is 2, this is 1, and this is 1. Okay, so our chain code is 0, 3, 0, 3, 2, 2, 1, 1. Okay, so this is our chain code. So I'm writing here 0, 3, 0, 3, 2, 2, 1, 1. Okay, so now we have to write the first difference. So how many steps we need to traverse from 0 to 3? So when you will count, it will be 3. So how many steps is required to move from 3 to 0? So here, see, only one step is required to move from 3 to 0. So it is 1. Okay, then 0 to 3, it will be 3. 3 to 2, it will be 3. 2 to 2, so same number, so it will be 0. Then 2 to 1, it is 3. And then 1 to 1, it will be 0. And then we have to check the difference between the last element and first element as well. So we have to traverse from 1 to 0. So that will be 3. Okay. So this is our difference. Okay. Now we have to convert this difference to shape number. Okay. So what is the smallest number we can generate from these digits in the circular sequence? So you can guess that number will be smallest only when the smallest digit will be at the most significant bit. So if the shape number will start from 0, then there will be the possibility that number will be smallest. So we can start from here. Okay, so 0 3 0 3, and then we will move in the circular sequence. So it will be 3 1 3 3. Okay, so just verify here. This is 0 3 0 3 3 1 3 3. Okay, so this is the shape number. Okay, how we can find the order of the shape? So order of the shape is nothing but the number of digits in the shape number. So you can check this one here: 1 2 3 4 5 6 7 8. So order is 8. Okay, you can count here as well. Shape number is 1 2 3 4 5 6. So order is 6. Okay, it's very simple. So this much for this lecture. I hope I am clear to you. If you have any doubt, you can ask in the comment section. Thank you.